Hello, my name is Jean-Christian Gagne, and I'm going to be talking about my project, which was optimizing natural machine translation, partly using Python and TensorFlow. Here is a summary of my presentation. First, in the introduction, I'll give a background into machine translation systems and what they're currently being used for. Then I will go into autoencoder machine translation systems, how they differ, a little bit into how they work. Then I'll go into some issues that arise from using these autoencoded neural networks and how to optimize and eliminate these issues through TensorFlow and Python programs. Next, I'll go into my algorithm, specifically my recurrent neural network autoencoder, which uses two RNNs, one for encoding, one for decoding. I'll go into the math and code for that. Then I'll go into LSTMs, long short-term memory systems, a little bit into how they work, then attention mechanisms, a little bit into how that was used in my code. Then I'll actually go into my experiment, specifically what were the values of my hyperparameters, how big was my network, how long did it train, which data set I trained it on, how much of a data set did I use, as well as specific values that were used during training of both the encoder and the decoder parts of my code. Next, I'll talk about the specific results and how my system reduced the loss overall through step by step as it trained by using optimization, and how these results could be better by using more optimization functions as well as improved hardware. Finally, I'll go over specifically how the optimization techniques that I used improved the overall common approach to neural machine translation through autoencoders, as well as some specific optimization techniques that I didn't use but I do know about, and we'll go into a little bit of information on those that can be used for future work and further improving the naturalness of machine translation. Within the past few years, neural networks have been used to improve machine translation systems by coming up with new ways to synthesize compound words, the use of transliteration, and parsing of multilingual sentences. Neural networks have also been improved through the use of sequence-to-sequence models that use two recurrent neural networks through the use of multiple LSTM cells within those RNNs, and also the use of attention mechanisms. Using a combination of these approaches, neural networks train faster and more efficiently, and therefore output more natural translations of sentences. The most commonly used neural machine translation models use autoencoders to improve translation accuracy. The encoder part of the autoencoder is used to read each sentence in one language, encoded into a fixed length vector. Then during training, each part of the sentence is given a binary value that matches it to another part of a sentence in another language, and these binary values make up a fixed length vector. The decoder of the autoencoder then takes this vector and matches it to other binary values in another language, thereby translating the sentence. Since autoencoders are commonly used, an issue that arises from converting sentences into fixed length vectors is that if the sentence is very long or very complex, it becomes very difficult to differentiate between the two different languages through the binary vectors. To accommodate this issue, I used a combination of bucketing, padding, an atom optimizer, and other TensorFlow techniques for optimization. Using these techniques allowed me to minimize the loss and perplexity of the training of both the encoding and decoding of my network. I further showed that through these optimizations, I was able to get more accurate and more natural sounding translations from one language to the next. I trained my network specifically on English to French translation and was able to reduce the loss substantially per 200 steps, and each sentence was also fairly accurate in its translation. My RNN autoencoder uses two RNNs. One network to encode a variable length sentence into a fixed length vector, and then the other RNN network to decode that vector into a variable length sentence in the target language. The encoder reads each symbol of an input x of t, and then the hidden state of the RNN updates using the first equation you see there. ht equals f of ht minus 1 x of t. The decoder generates an output by predicting the next symbol yt given the hidden state ht. The decoder is also conditioned on yt minus 1 and on the summary c of the input, and the hidden state at time t is computed by the second equation you see there. ht equals f ht minus 1 yt minus 1 c, and the next symbol is thereby calculated using the probability of yt given yt minus 1, yt minus 2, etc., down to y1 and c, which equals g, another function, ht yt minus 1 c. F and g are both the activation functions that I use in my code. The figure on the right is a graphical representation of the RNN autoencoder. Both RNNs are trained at the same time to maximize the function given as, on the bottom left, the max of theta 1 over n, summation n equals 1 to n, log of the probability of theta of yn given x of n, where theta is a set of model parameters and xn and yn are the inputs and outputs to be trained on. In my code, I used an atom optimizer to estimate the model parameters. Once the RNN autoencoder finished training, it can be used to generate a sentence in the target language given an input sequence in the source language. LSTM stands for long short-term memory, and LSTMs are commonly used in RNNs for long-term dependency to remember information for long periods of time. The LSTMs used in my RNNs are used in a chain of repeating modules within each neural network, like you see in the figure on the left. The attention mechanism that I implemented uses a multi-layer sequence-to-sequence LSTM network, depicted in the figure on the right, to allow the the decoder to decide which parts of the source sentence to pay attention to. This attention mechanism allows the encoder to encode less information from the source sentence into a vector, thereby reducing the computational cost of the encoder while maintaining the accuracy of an autoencoder without an attention mechanism. When I ran my code, I trained my autoencoder on English to French translation using TensorFlow as Python as the basis for my code. I used the bilingual parallel corpora from ACL WMT15 to train my network on English and French. My autoencoder was trained using 2 layers of 256 nodes for 20,000 steps. The results and charts in the results section of this presentation correspond to this reduced network, and as such, the results could have been better with a bigger network using more robust hardware. As far as the data set goes, WMT15 is made up of the following English to French parallel corpora: Europarl, which is made up of 61 million words; news commentary, which is made up of 5.5 million words; UN papers, which correspond to 421 million words, and 2 other corpora, 90 million words and 272.5 million words, totaling 850 million words. Now, I couldn't train my network on 850 million words because of my hardware restrictions, so I reduced the size of the data set to 22 million words. After tokenizing the words during training, I used 40,000 of the most frequently used words in each language to train my encoder and decoder. Any word that is not included in this 40,000 words is mapped to an unknown UNK token. Now, the training parameters I used when training my autoencoder was 2 layers of 256 with a batch size of 64 to ensure that each side, the encoder and the decoder, was trained the same using the same data set. I set the learning rate for each network to 0.1 and the learning decay rate, gamma, to 0.99 in order to optimize the rate at which the network learned. During training, every 200 steps, the network's weights, biases, loss, and learning rate were saved in a checkpoints directory in order to ensure that the network could be stopped at any time to test the accuracy of the translation. My code actually has no stopping point and can continue to train theoretically infinitely. It has to be manually stopped in order to begin decoding. So I stopped it after 20,000 steps. The basic tokenizer and atom optimizer functions from TensorFlow were used to optimize the code and minimize the loss between each step. If you want further details on my code, you can visit my GitHub page, which I will provide at the end of this presentation, as well as the website for where I got my actual data set. The chart on the left shows the loss for both a common autoencoder network, shown here as the orange line, and the optimized autoencoder network that I created, depicted here as the green line, for 20,000 steps of training. Now, as you can see from the graph, the optimized autoencoder that used an atom optimizer, attention mechanism, and slight changes to various hyperparameters reduced the loss by about 100 per 200 steps. This reduction in loss is about 46% improvement on the common autoencoder network, and thereby has the potential to outperform most of the autoencoder networks used today. This common autoencoder network was coded through a tutorial that I found on TensorFlow. And what I did was I added various optimization tools to the code to further improve it and reduce the loss. In both cases, both the common and the optimized autoencoders were able to translate short sentences, no matter their complexity, very well. But the optimized autoencoder was able to translate longer sentences a little bit better. The translation quality and speed could have been further improved by adding better hardware to my current PC, like a faster processor, access to more cores, more RAM, and this would thereby allow me to train a much bigger network than 256 nodes, 2 layers. So I could add layers and nodes and thereby train on a much larger data set. This would substantially improve the accuracy and natural sounding value of the translation from English to French. The only other way I could see to improve my results would be to let the code run more than 20,000 steps. But given my current hardware restrictions, it took about 12 hours for the code to train just to 20,000. So the idea of training it longer didn't seem feasible. Since autoencoder neural machine translation models are being used more and more, the question on how to optimize these models arises more frequently and should thereby be further looked into. In my presentation, I only outlined the optimization techniques that I used: an atom optimizer, an attention mechanism, bucketing, and padding. The atom optimizer lowered the overall loss of the network. The attention mechanism improved the efficiency of the network by reducing the computational cost of the autoencoder. And the use of bucketing and padding improved the network's handling of variable length sentences and variable complexity sentences. These are only a few of the known optimizing tools offered in both TensorFlow and Python. WMT15 has an updated version of the basic tokenizer function in TensorFlow that is much faster and more efficient. There are different math functions in TensorFlow that can also be used as loss or activation functions, like mean squared, tan, sigmoid, etc., to further optimize the minimization of loss and the efficiency of the overall network. You could also add a second queue network to the autoencoder that would make the network more stable and reliable during its training and learning process. If all the optimization tools mentioned and available were used in conjunction with better computer hardware, the resulting autoencoder would produce translations that rival that of natural human translation. As stated earlier in this presentation, here are the links if you would like further information. The first link is where I got my data set, and the second link is the GitHub link to my code.